So what we can do is use our same strategy for attacking this. Basically, we have our same our same basic setup. I'll go back to this diagram here. So we had our thetas, t minus 1, t, and t plus 1, our observations, xt plus 1 and xt. So this line right here is where we subdivided the total probability of all of the observations, okay? So what we really need to do is be able to subdivide the probability, because basically what we've got we want to get P of theta t given the entire observation vector. So let's apply Bayes' law to that. Let's write it in the simple form that we used in the previous case of just the joint probability that. So our denominator, we're good. We've already got that. What's challenging is this numerator. So immediate and obvious question about the numerator, is there any way that we can relate that to our forward probability summation? Is there any way, for example, that we could factor this so that at least part of that would be our forward probability summation? Well, if we look at our diagram here, that's basically what the diagram is already showing us. That little line right there is dividing the total probability of the entire observation sequence into two parts. The part up to xt and the part after xt. Or maybe to state that slightly differently, all the way up to theta t and everything after theta t. So another way of seeing that is as an equation instead of a picture. I'm just going to take this numerator and I'm going to divide it into two parts. So I've got theta t, comma xt. What's that? That's the forward probability summation that we already figured out how to compute. Okay? So now what's everything else that's left in order to give me this total joint probability? What do I have to write after it? P of something given something. Maybe something, something. What's left? Well, again, we can go to our picture. So what's in the picture here? Well, there's a bunch of xt's, right? There's xt plus 1, t plus 2 on out, right? So looking at this, we don't want any more thetas, right? We just want x's. So it's just going to be x from t plus 1 on up to n, and now it's going to be conditioned on theta t. Okay, so this part is referred to as the forward probability component. This part is the backwards probability component, and we can derive that backwards probability component by the exact same analogy that we used for the forward probability component. So so here's what we just went through. We took this and we broke it into two parts. There's the backward probability component. There's the forward probability component. And now we got to get that backward probability component. So the obvious analogy is we're going to want to compute this by summing over the variable that comes after theta t. So we just do the exact same thing. We take what we want to get, we write the exact same thing for one step forward, and we say, what are the missing pieces? If you look at this picture here, so if we look at the picture of what's missing, that's the line that we already drew. This is the line that's one step forward. So the only pieces, again, that are needed to add are that piece, the transition, that piece, the emission, and then we're going to sum over theta t plus 1, and we'll get exactly what we want. That's the picture version. Then there's the equation version. So this is what we want to get. We write the exact same thing one step to the right. In other words, t plus 2 instead of t plus 1. And then we just toss in the remaining pieces that we needed. There's the transition, there's the emission, and now we got to get rid of theta t plus 1 that appears in here so that only theta t appears. Easy to do. We just sum over theta t plus 1. Okay? So this is what's called the forward and backward algorithm. The reason this is called the backwards probability summation is you have to compute it backwards. In other words, it's trivial to compute for theta, basically theta n, okay? Then we can compute it for theta n minus 1. Then we can compute it for theta n minus 2, all the way back to theta 1, okay? So it has to be computed backwards. Then, to compute the posterior probability for a specific theta t conditioned on the entire observation sequence, it's simply the product of the forward probability up to theta t, the backwards probability after theta t, just divided by the total probability of the observations, which we already got from the forward probability summation. Okay? This gives you the ability to compute the posterior probability of any hidden state conditioned upon the complete set of observation data. I'll put up some additional videos, as I said. Please take a look on CCLE for any further clarifications that you may be wanting.